myself Vikas Gupta, and today I'm back with experiment number 2, the digital signal processing lab. Which is today's aim of the experiment is to study the performance of the below given filters using a real-time PPG signal recorded using a PPG sensor as well as using the given recorded ECG signal. So let's get to know what is PPG signal. PPG stands for photoplethysmography signal, which measures the volumetric change of the heart by measuring the amount of light transmission or reflection. As the heart contracts, the blood pressure within the left ventricle of the heart increases. This increase forces a pressurized pulse of blood into the arteries throughout the body, which causes them to swell slightly before once again returning to their previous state for a certain amount of time. Thus, by simply shining a light on a patch of skin under these arteries with an LED light source, the increased pulse pressure would be measured by measuring the amount of change in the light reflected back onto or transmitted through to a light sensor. So, the LED light should be placed in an area where arteries are close to the skin for better measurement, such as finger tip or any ear. And the amplitude of the signal is directly proportional to the pulse pressure. So the higher would be the peak in the graph of the PPG, or the higher or the stronger pulse. Each peak in the resulting signal can be identified by a special heart rate algorithm that determines the amount of time that would occur between each successive peak, thus giving us the measure of the heart rate. So moving on to the experiment. The first experiment is to get the rate of high frequency noise, the smoothen out the signal which could be easily achieved through the moving average filter. So this experiment is quite similar to the last experiment, except here we are going to use the real-time PPG signal, which could be realized by slight changes in the previous code. In this code, we are going to use the pin A0 of the Arduino Duo board to measure PPG signal. And here, we are going to consider fixed number of samples to be recorded, to be fed, to be recorded beforehand. Here we are considering 1000 samples to be recorded. And in this loop, we are going to read the PPG signal at every 1 millisecond, every 10 milliseconds. And once we are done with 100,000 samples, we are going to perform the moving average algorithm to smoothen out the signal. Here we are considering the FRAC value as 0.008, that is of about 8 samples out of 1000 samples as a window to calculate the moving average and smoothing the signal. So moving on to the output. This is the output of the previous code. This blue signal is the original PPG signal which we recorded using the PPG sensor, and this red one is the smoothened version of it. And here we took the window as 8. Moving on to the next experiment. The aim of this part is to emphasize the high slope portion which could be easily achieved through derivative filter. Here also we are going to use the live recorded PPG signal which could be done using the pin A0 of the Arduino Duo board and similarly recording the pulse. So moving on to the next experiment. And let's see the output of this part B. As you can see, this blue colored signal is the smoothened version of the recorded PPG signal, and the green one and the red one the first order difference filter output and the 3-point central difference output. The aim of the part C is to design a moving average filter with a floor value of 0.8 into total number of samples which we consider here to be 1000 to extract the baseline drift component from signal as well as to get the signal corrected. So here we are also going to use the pin A0 to measure the signal of the Arduino Duo board. We are going to use the same loop, the command analog read, which basically reads the analog signal from the sensor and stored in the array X of 1000 samples. Now we are going to feed both this recorded signal, the moving average filter with a window of 8 as well as 8000. The purpose of feeding it to the 8000 is to get rid of the high frequency noise, and to feed it to the 8 is to smoothen it out. And finally, we will subtract the both to get the baseline drift. The output is as follows. The blue colored line is the original PPG signal measured using the sensor, The red version is the corrected PPG signal without noise as well as the baseline drift, and the screen signal, which is a slowly varying signal, is none other than the baseline drift, which was present in the blue signal. Final part of the experiment, which is to get the output of a system in which we first perform the first order derivative filter on the PPG signal, followed by performing the moving average filter with window value 8. Here also we are going to perform the same thing. We are going to record the PPG signal beforehand for 1000 sample in the real time using the analog read command, and by followed by passing it to a first order derivative filter, which is as follows to get y of I, and this y of I is then fed to moving average filter of a small window of it just to smoothen out the signal. The output will be as follows. As we can see, this blue colored signal is none other than the lively recorded PPG signal. This red colored signal is the first order difference filter output, which is then smoothened out using the moving average filter with Windows 8, which is the screen signal. Now, let's move on to the ECG filter. This graph basically shows the output of the moving average filter. Here, the blue colored signal is none other than the ECG signal, which is given to us beforehand, and this red color one is the smoothened version of it. Now, we are going to solve the part B of this experiment using the recorded ECG signal, which is to get the first order as well as the 3-point central difference output of the ECG signal. Here, the blue colored signal is the original recorded PPG signal, which is given to us beforehand, and this red colored one and the green colored one is the smoothened version of the first order difference filter and the 3-point central difference filter output. Here the blue colored signal is the original ECG signal, and the red color signal is the ECG signal, which is free of noise as well as free of baseline drift, which we have achieved using the same algorithm as we used in the part C of the experiment number 2 in the previous slides. And this green color signal, which is a slowly varying signal, is the baseline drift, which was present in the ECG signal before removing it. And finally, we have realized the part D signal, which is basically a system in which the derivative filter and the moving average filter is cascaded in the following order, such as this is the original ECG signal, is a blue color one, where we can see this slight high frequency noises, which is then fed to the first order derivative or difference filter to get this region. As you can see, wherever there is a high peak, we will also get a higher value at the first order derivative filter, which is the very function of this derivative filter. And finally, we smoothen out the signal using the moving average filter with window value 8. And we can see as we smoothen out the signal, this peak basically gets a normalized value. So thank you for listening. Goodbye.